Today we're going to do a lesson that's kind of like a little bit of a pre-6 simplifying square roots, just to make sure we're understanding a few things about some stuff in the past that you've learned, and just so we can kind of make sure that we are good to go. The thing about square roots and radical expressions, we can add or subtract radical expressions basically in the same way that we combine like terms. So for example, 5x plus 4x equals 9x. If we have radical expressions with the same endings, then we can add or subtract them just like you would your regular like terms. So the symbol that we see right here is called a radical sign. You see the little radical dude off to the side, the radical sign. Basically, it's used to represent the positive square root of something. So notice there's no symbol in the front, but when you see just the regular radical sign, that's the square root sign, we are basically looking for the positive square root. So for example, if I said, what is the square root of 16? With that symbol, the answer is 4. The next symbol you see here is the negative square root. So basically when you see that sign, what that is basically saying is we want to know what the negative square root of 16 is, which is now negative 4. Basically, if you remember, a square root means the number times itself that gives you the number underneath. Speaking of the number underneath, the number under the radical sign is called the radicand. So you'll hear this term throughout the rest of this year from different times, but the radicand is the number that's under the radical sign. The other symbol that we do sometimes see is this, plus, minus, square root of 16. Basically, the plus or minus the square root of 16 is kind of saying what it sounds like. It wants both the positive square root and the negative square root of 16. Well, we know that 4 and negative 4 will give me 16 if I multiply them by themselves. So our answers would be 4 and negative 4. So here we are adding and subtracting some square roots. So we just mentioned this a minute ago. Basically you can add radical expressions, things that have radical signs, just like we do with our regular like terms. So what we will want to look for is things that have the same radical expressions as factors. So just like 5x plus 4x equals 9x because you can add the coefficients, what we want to do is look at how to put together things like this first one. So 5 square roots of 2 plus 4 times the square root of 2 basically means we have square roots of 2 in common. We add the coefficients together, and 5 plus 4 is 9. And that would be simplified and complete. For the second equation, again, we have square roots of 3's. And if we're adding or subtracting, we look at the numbers in front. 2 minus 7 would give me negative 5 times the square root of 2. If I move on to the next one, here we have the square root of 5 plus the square root of 5. The square root of the 5 plus the square root of 5 would really be 1 square root of 5 plus 1 square root of 5. So kind of like kind of like x plus x is 2x, we would get 2 times the square root of 5. If I move on to the next one, we would have the square root of 10 that we are adding together. And again, we would have 10 square roots of 10 because we would be adding just the coefficients. And lastly here, we would have the square root of 7, and we would have 2 minus 1 leaves me with 1 square root of 7, or the square root of 7. So over here on the next, off to the side here with the right, do not assume that radicals that have different radicands cannot be simplified. So just because they both don't have the square root of 3 and the square root of 3, or the square root of 5 and the square root of 5, you don't want to assume that that means they can't be simplified. If you look at this one here, we have 2 square roots of 4 plus a square root of 1. We can easily simplify that because we know the square root of 4 is 2, and we know that 2 times 2 is 4. The square root of 1 is 1, so 4 plus 1 equals 5. So as much as that looks like maybe I can't do this, that basically becomes 5. So the next one is kind of a tricky one, I think, for some people. We're going to try to simplify square roots. To be able to simplify square roots, obviously you can use calculator at times, but there's going to be lots of times that we just want to work with simplifying them and not necessarily coming up with the decimal representations. But we must be familiar with our perfect squares to be able to do simplifying square roots. So let's get a little bit of a list here for our perfect squares. So perfect squares basically means numbers that when I take the square root, I get a nice whole number integer. So square root of 1, 4 gives me a 2, 9 is a perfect square because 3 is my answer when I take the square root, 16 gives me a 4, 25 gives me 5, 36 gives me 6, 49 gives me 7, 64 gives us 8, 81 gives us 9, 100 gives us 10, 121 gives us 11, 144 gives us 12. Now certainly because of our basic multiplication tables, we should easily know through 144. We should also think about other ones that are kind of helpful. For example, if I thought of 20 times 20 is 400, so 400 is a perfect square. We want to think of numbers that are a little bit easier as we just get bigger and bigger and go forward. But knowing these perfect squares is going to help us simplify the following expressions. So to simplify square roots that are not perfect squares, we're going to use what we call the product property. Okay, so here's a little bit of a box to kind of explain what that means. So in algebra terms, if I had the square root of something where x times y were my two factors, I could kind of break this apart. The square root of x times the square root of y. So if I can do something with the square root of y, I could break it apart and kind of simplify it. If I could do something with the square root of x, I could break it apart even if the thing underneath isn't doable. We also have to keep in mind that x and y are 0 or greater. Reason being is I can't have a negative and take the square root of it. So I have to have them both being 0 or greater. So what does that look like as far as numbers goes? Well, here would be an example. So let's do the square root of 108. Well, if I look at my perfect squares up above, 108 falls in between 10 and 11. But I can look in simplifying this a little bit more. So here's how I do this. So I just look at, using that product property, some numbers that will go together that maybe will help me. So I'm just going to start with 2, because I know 2 goes into 108. If I do the square root of 2 times the square root of 54, that's the same thing as saying the square root of 108. Well, neither of those is perfect squares either. So I'm going to go a little bit further. 2, I'm going to break 54 up into 6 times 9 to see what that looks like. Well, I see a perfect square. So that is something that we're going to be able to do something with. My next step, though, is I see 2 and 6. So some of us are going to say, oh, well, I can't do anything with that, so we're done. Well, not really. If I go back to breaking this up further, I have the square root of 2. 6 becomes the square root of 2 times the square root of 3. And remember that square root of 9 comes down now as 3. So I can take it out of the square root sign because we've done the operation of square root. So next I want to look at and focus on these two numbers right here. Square root of 2 times the square root of 2. If I go in reverse order as what we saw over on the algebra side, becomes the square root of 4. Square root of 4 is 2. So when I see something that's the square root of something times the square root of itself, basically what's happening is that the square roots kind of undo each other. And I end up with 2 next to the square root of 3, because it doesn't have something to go with, times 3. I could multiply 2 times 3. Can't do anything else with the square root of 3. So I get 6 square roots of 3. So that's as far as we can go. That would be the answer. So now I want to try a few of these. So looking at the square root of 50, I think I'm going to break it up into 2 and 25. Ideally, you're going to start trying to get good at noticing perfect squares as factors. 25 becomes 5, and so my answer is going to become 5 square roots of 2. Not the only way you could have gotten there. You could have gone 5 times 10, and then 5 times 5 times 2, and you could also get to that answer, but we should still get the same answer. Number 24. Again, there's really no right way to do this, but again, if I'm looking for perfect squares, I see the number 4. Square root of 4 is 2, and then the square root of 6 can't go any further, so it stays as 2 square roots of 6. So the more you kind of practice this, you'll start to kind of figure out how this is going to be easiest for you. Square root of 45. Well, again, I know my perfect squares, so I know the square root of 9 times the square root of 5 will give me the square root of 45. When I take the square root of 9, I get 3. Square roots of 5, can't go any further with that. 98 is a little bit trickier because I don't see something right away. So I want to think of all my divisibility rules. Well, looking at that, I don't see anything that jumps out fast, but I do know it's an even number, so I'm just going to take 2. Well, look at what happens. If I do 2, right away we get 49. That's a perfect square, so I'm going to get a 7 times the square root of 2. Just like with our variables, we're going to put that whole number 7 out in front. A couple of reasons. If I put it in the back, it might be confusing. If I don't write it correctly, it might look like the square root of 27. So 7 square roots of 2. So next we want to look at simplifying square roots that are not perfect squares by using the quotient property. So first we talked about the product property, now we're talking about the quotient property. Well, basically in the algebra look would be some sort of a fraction that looks like x over y with the square root radical sign over on the outside. Basically that would break down to the square root of x, square root of y separately, and then we can reduce from there. Okay. Basically on this one, x and y are both greater than 0, but also y cannot be 0. Reason for that is because obviously if y is 0, we're dividing by 0, which we cannot do, it's undefined. Okay? So here would be an example of what this might look like. If I had the square root of 3/4, well, I don't know what the square root of 3/4 is, but to simplify it, I'm going to treat each, the numerator and the denominator, as 2 separate perfect squares. I see the denominator right here is a nice perfect square, so I'm going to say square root of 3 over 2, and that's your most simplified answer there. So looking at the bottom 2 examples here, again, I don't know what the square root of 11/16 is, but if I focus on just the numerator and the denominator separately, I do see a nice perfect square down in the denominator. So my answer is just going to be square root of 11 over 4. And when I go to the second one, again, I don't see any numbers that I would know off the top of my head for 35, but I do know that the square root of 36 is a perfect square. So the square root of 35 over 6 would be simplified. 2 more examples here. Again, the square root of 13 over the square root of 4 will start to help us break it down a little bit, and the square root of 13 over 2 would be our final answer for that. And the last one, we just got to think about what this is really saying to us. Square root of 5 over the square root of b squared. Now let's think about that for a minute. So b squared, whatever b is, there are 2 of them. There are b times b. So once I take the square root of b squared, notice that that becomes b. Hopefully the big idea out of this little note sheet is really that if I have the square of something and the square root of something, they're undoing each other. So if somebody says to me the square root of b squared, the answer is b. If I take the square root of b and square it, the answer is b. So squares and square roots are undoing each other. So this next little part here is just a little bit of a review on your exponents, just to make sure we understand this. The power is the product of repeated factors. The base, remember the base here is the number that is being multiplied over and over and over again. The number of times would be the exponent. So in this first example, the power is the entire 1/2 to the 5th power. The exponent is 5, which means it's 1/2 times 1/2 times 1/2 times 1/2 times 1/2 5 times. So just keep that in mind. Writing each product using exponents. Now, so this is an important piece right here, and I think I want to really spend a couple seconds talking about this. So -7 times -7 times -7. So the exponent is going to be -7 to the third. Notice how these are in parentheses. So notice how this answer is in parentheses. When I have a negative as my base, one thing that I really want you to do is to make sure that it stays inside the parentheses. And here's a reason why I would do that. So let's say we had -7 squared. Okay, one thing that I think sometimes we look at, and we would see this, and we'd say, oh, -7 squared is 49. Well, there's a difference here, because if I was to write -7 squared like this, those are two different answers. When I write -7 squared, remember the exponent is going to whatever it hits first, in this case the parentheses. Over here, the exponent hits the 7, not even the negative, just the 7. So when I look at my answers to these two problems, -7 squared without the parentheses would be -49. -7 with parentheses squared is a +49. Very, very big difference there. What I want you to do is anytime you have negative bases or fraction bases, to make sure you have parentheses around those bases to make sure that we are being as exact as possible. So again, here is kind of what I was just referring to. So we have a -2 to the fourth inside the parentheses. This expanded out really looks like base of -2 times -2 times -2 times -2 is 16. Compare that to the second one. -2 to the fourth without parentheses is basically saying our base is a 2. So it's really negative times 2 times 2 times 2 times 2, which is going to stay -16. Now this is really going to be a difference, obviously, when we have even exponents, because the negatives will pair up and make a difference. Not so much on the odd exponents, but I think it's a good habit to get into, just to do it the right way every single time. And basically, just to help finish our review, just want to talk about negative and zero exponents. Remember, our zero exponents for any non-zero number, any number to the 0 power is 1. The only time that that's not going to happen is over here. If 0 to the 0 power we call undefined. Any number, though, other than that, and that includes exponents, if it is to the 0 power, it is the answer of 1, not 0. For negative numbers, don't forget, we don't have a negative exponent giving me negative answers. What it is giving me is the reciprocal of our base. So you'll notice in the example here, 4 to the -2 power. Basically, that is saying 4 over 1 to the -2 power. And if I take my base and flip it upside down, it becomes 1 over 4 to the second power. And now it's a positive power. The only restriction we have on this one over here is a's can't be 0 again, because then I'd flip it over and have the zeros that I'm dividing by, which I can't do. Okay? So we just want to make sure that we are understanding of that. Some number like this one over here, 1/3 to the -2nd power, I would flip my base over to make it to the positive second power, which then means 3 squared, which is 9. So here would be another kind of example that you could see if that helps in some way. So 1/3 to the -2nd flips it upside down, then it's now a positive, and then 3 squared is 9. Okay? So then evaluating some of these expressions down below here. So evaluating the expression, if I have a negative, what I'm going to look to do here is we're going to take 2 to the -5, so I'm going to flip my base over, and it's now to the +5. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Notice how the answer did not go negative. Okay? On the second one, notice here now, this -2 is going to hit the 5 first. So the negative is going to stay out in front. the base of a 5 over 1 becomes 1 over 5 squared. But notice now we do have a negative, but it's not because of the negative exponent, it's actually because the negative is not in parentheses. So this is going to give me an answer of negative 1/25. On the next one, I have 1/6 to the negative third power. Again, the base flips over, becomes a positive exponent, and then 6 times 6 times 6 is 6 cubed, or 216. 5 to the 0 power, automatically 1. Do not make the mistake of thinking the answer is 0. And I go to the second one, I have 2. 3 to the 0 power is 1. 2 times 1 is 2. Being able to work with all these exponents is going to be crucial to your success this year. So it's important that you understand them, that you work with them. The negative exponents are not making our answers negative, but it's doing the reciprocal of the bases. The 0 exponent is making our answer become 1 unless it's a 0. Being able to simplify radicals and our square roots as much as we can, and combining them is going to be very, very important. So it's a really, really critical section that you kind of get yourself ready for the rest of this chapter.